All right, welcome to the Notes 4.2 Part 2, where we're going to continue to talk about the Bohr model. And this would be under the question that says, what happens when electrons move inside of the atom? And Bohr came up with 3 rules, and I think it's important that you write all 3 down and that you don't paraphrase too much. So here are the rules for the Bohr model according to Bohr, who is pictured here at a much older age than your original picture in your notes. Number 1, he said electrons have a specific amount of energy at each energy level. So we kind of talked about that already, and we already talked about how that increases as you move away from the nucleus because electrons like to be close to the nucleus since they're oppositely charged. Number 2, this is a biggie. Bohr said that electrons cannot be between energy levels. They must either be first energy level or second or third, etc. They cannot be in between energy levels. Even though there's space there, they cannot be there. And so he pictured that as climbing up a ladder and standing on a rung. You either are standing on a rung or you're not. You can't be between rungs on a ladder. Electrons are the same way. And then finally, electrons can move up or down the ladder, so to speak, but to do so, they're going to either absorb or release what's known as a quantum of energy to do that. So electrons must absorb. If they absorb energy, they're going to go up an energy level, or release to move down an energy level, a quantum of energy. And a quantum just refers to a specific amount. And I'm trying to keep reminding you guys of this, but this is all tied back to our discussion about light. And so Bohr figured this all out based on measuring the energy of photons. So we'll talk about how he did that in a second. So he said, electrons have a specific amount of energy at each energy level. They got to be in an energy level. They can't hang out in between. And then if they need to move around, in order to move around, they're going to either absorb quantums to move up energy levels, or they're going to release quantums to move down energy levels. So let's talk about the consequences of these rules. I would like for you to draw a picture. We've got the Bohr model here, talking about what happens when electrons move inside an atom. Draw the Bohr model of a lithium atom. Now here in the nucleus of your lithium atom right here, you have 3 protons and you have 4 neutrons. Now that's really not important. That's just the nucleus. And as you can see, nothing's changing about the nucleus from start to finish. So you're going to start with 3 protons, end with 3 protons, start with 4 neutrons, end with 4 neutrons. So I don't mind if you just put a nucleus. But what's important here is that you guys see in the first energy level, we have 2 electrons, maximum number of electrons that can be held in the first energy level. So 1, 2. And then because that's the maximum number, the third one would go in the second energy level. And the nucleus is way too big in this drawing. It's not to scale, but that's okay. This is called the ground state, and I want you guys to write that down, and the ground state has a definition that's super important, and that is when all of my electrons are in the lowest energy arrangement or combination they can possibly be in. There is no way that I can take these electrons and put them in a lower energy arrangement. You've got 2 of them in the first energy level. There's no room for a third. And so that one is going to go in the next best location energy-wise, which is the second energy level. So that's the lowest energy arrangement of electrons. When energy is absorbed, and to make this even better, I'm going to say quantum of. When a quantum of energy is absorbed, one of those electrons, the amount of energy would kind of dictate which one. In this case, we're going to take this electron here, our outer electron, which is actually known as a valence electron, is going to absorb energy. And remember, that means that it's going to be able to move farther away from the nucleus, or out. And so when it does that, it moves out to the third energy level. And because it's no longer in the ground state, this is no longer the lowest energy combination, we call this the excited state. where the electron jumps to an outer energy level. So the excited state just means that it's not in the lowest energy arrangement. So it's not the ground state. So if it's not the ground state, it's the excited state, which just means it has more energy than it has to. If you look at this diagram here in the upper part of the box, you can see a photon hitting that electron on the stairs, and by doing so, it moves up the stairs. And so that is how Bohr pictured it. And then in part A here, same kind of situation. Electron is moving up 1 or 2, or it could be even more energy levels depending on how much energy it's absorbing, and then it would fall back and release a photon of energy as it falls back. Now I want to talk about this absorption of energy. Electrons don't really like to hang out in the excited state because it's a higher energy than they need to be. And energy being high is not something electrons like. They are pretty lazy, and so they'll like to come back down to their ground state. And so when that happens, what we have is the exact opposite process here, where that excited state electron out in the third energy is going to drop back down. And when it drops back down, so this guy right here, when he drops back down, he's going to release a photon of energy. So remember, energy is released, and again, to make that even better, we could say a quantum of energy is released. And when it does that, a quantum of energy is released, and that's a photon, and that photon is going to show up. We could actually tell what type of photon it is, how much energy it has, how much, what its frequency is, and what its wavelength is on what's known as a bright line or BLS spectrum. Bright line spectrum, BLS, bright line spectrum. So BLS. So a bright line spectrum is how we can tell how much energy is being released. And based on how much energy is released, we can really tell what kind of energy is being released. Here's an example of 3 different types of spectra. And a spectra is just something that shows all of the wavelengths, or of the possible wavelengths. You have a continuous spectrum at the top that would show, and this is just visible light, because obviously that's the only type of light that our eyeballs can process. So up here we have all the wavelengths. In an emission spectrum, this is a bright line spectrum that we were just talking about. These are wavelengths released. And in an absorption spectrum, these are the wavelengths absorbed. And because we have those 2 equations, if we know the wavelengths that are released, then we can also know the frequency, and we can know the energy of those photons that are released. And so this bright line spectrum is the one that we really want to focus on here. And as you can see, it looks like some bright lines. And these are the quanta. These are the energies of the photons released when those electrons move from the excited state back down to the ground state. So I'm going to even write that over here. So that's going to be going from excited, the excited state, back to the ground state. The absorption lines, you'll notice, are all of the wavelengths, but the ones that are missing are the ones that are picked up by the electrons. So they're absorbed. So they look like they're missing. So that would happen when you have electrons going from the ground state to the excited state. We don't really use that one as much. Mostly we're going to be concerned about the emission spectra, and that's because the absorption is just the opposite. So those lines that are black are the lines being emitted in the bright line spectrum. And that's what helped Bohr decide that these electrons must be falling an exact distance to give them an exact energy. That's all for now. Thanks for watching. Have a great day.